Okay, I will start first. Um, so good afternoon, everyone. So today our topic is vibration analysis using the matrices method. So this is our group member. My name is Chu Isang, matrix number 222957.
My name is
Okay.
Mohammed Azam. My matrix number is 222259.
Okay, my name is Tanlia. My matrix number is 225538.
So before we move on, we need to know what is matrix. So matrix is a 2D array denoted as A, I, J. Represents equation with row and columns. A is for equation, I is for rows, and J is for columns. It is too versatile to an extent. It could solve a linear equation, transformation in physics, engineering, economics, statistics, and various mathematical applications.
So what is an vibration analysis? Vibration analysis is a mathematically representation of vibrating system involves mass matrix M, stiffness matrix K, and damping matrix C. For problem solving, the system's equation of motion must be in matrix form, capturing the physical interaction. So this is the equation of motion of vibrating system. Mu plus Cu plus Ku is equal to Ft. M represents mass matrix, C damping matrix, K stiffness matrix, and F is force matrix, and the last is U is the displacement matrix. So this is the importance of vibration analysis. The important is the time domain vibration analysis monitors the level over time, setting predefined limits for acceptable operation based on its standard data. So if we exceed the limits, it might result in the broken. So frequency domain analysis excels in detecting abnormal patterns, uncovering hidden defects like bearing issues by analyzing the frequency spectrum, overcoming obscurity in time waveforms.
Okay, I'm Yang. So now I will present the application of vibration analysis in structural engineering. So as we can know, structural engineering is more to civil engineering side. Okay. In structural engineering, we will learn how to analyze the safety of the building. Yeah. So now we can apply the vibration analysis in structural engineering. So as you can see the example, okay, from the example, this is a diagram. This is a diagram that demo the situation of the object or molecule in the building during the external force is applied on it. So from here we can see that they have a formula mx plus tx plus kx is equal to the force. So m is the mass, c is the damping coefficient, k is the stiffness, and also s is the velocity, s double dot is the acceleration. Okay, so now we move to the next slide. Okay, from here we can see that actually I think all of you know what is the Newton's second law that we have already learned during secondary school. It is F equal to ma. So from here we will combine what we have learned before and also the matrix together, and also the formula about the vibration analysis just now. So we can solve the problem. Okay. At the first, you can see that the equation is expressed in the linear form. From the linear form, we can translate it become the matrix form. So in matrix form, you can see that we like as usual. So you guys can see how we apply the matrix in the vibration analysis. So now we move to the but this is more about the concept. So now we move to example. Okay, it's a very simple question, and we given the m is equal to 2 kg, c is equal to 0.5, and s slot m, and also the k is equal to 10n slot m. Okay, we just substitute the value to the formula, and then we express the formula become matrix form. So from here we can know that this is a very simple example for all of us to understand how the vibration analysis is applied in our life. Yeah, thank you.
All right, so now I will present about the application of vibration analysis in the mechanical engineering. So before this, I want to share this question. This is undamped multiple degree of freedom. So to solve this equation, I have to explain that we are not using the general equation of motion, like stated before is mx plus kx plus cx is equal to ft, is some different. So here is how we derive the equation. So first, I would like to tell that the undamped means that there are no energy losses in the movement. So when we provide some disturbance into the system, there will no energy loss. So in the equation, we will not apply the Ft, means that the force applied to the system. So this is a free body diagram. So the Fg means that the gravity, Fn the normal, and the Fk is the force applied by the spring. So the spring force is always in a direction that tends to pull the system back towards the equilibrium. So that's why okay, before this, I have to tell that the sum of the force is equal to ma, which is the second law of Newton. F is equal to ma. So now we know that Fk is equal to kx. The k represent the constant spring and the x is displacement. So now we uh, now we replace the fx replaced by the fk. So that's why we put the fk is because the spring force or moment is in the direction that opposite of the displacement. So now we can derive the formula now, and then we get the mx plus kx is equal to 0. So by applying this general equation, we can solve this multiple degrees of freedom. So first, we need to derive the equation of the m1 and m2 by using the equation produced. So first one, we need to solve the m1 first. So how to solve this? So first, we write down m1 x1 because the deflection is x1. So the k1, which is the spring attached to m1, is also deflection by x1. So we plus k2. The k2 is compressed by x1 and is extended by x2. So this is the first equation. And we need to rearrange this like x1, x1, and x2, x double dot 1 and x1 and x2. So apply the same concept in M2. Uh, Here you can see there are two springs attached to the M2. So the first is K2, same the concept. The K2 is expressed by x1 and expand by x2. So but something different is x2 minus x1. So same, we rearrange the formula, then we get the second equation of motion. So now we transfer both equation to matrix form, and this is the matrix form of these two equations. So now we give a value to K1, M1, K2, M2, and K3. So K1 is equal to 1, K2 is equal to 2, K3 is equal to 2, M1 is equal to 1, M2 and is equal to 2. To solve this matrix, we need to solve the determinant of K minus omega square M. K represent the stiffness matrix and the M is the mass matrix. So now the K is, since I already calculate the value for this is 3 minus 2 minus 2 and 4 minus omega 2. This is the mass matrix. So this is the determinant we need to solve by applying the determinant like 3 minus omega square is time to 4 minus 2 omega square and negative 2 times negative 2 and then we got this equation. Then now we need to solve the quadratic equation by let omega power 4 is equal to a. Then we solve, and then we will get the omega value. Omega value, it means omega value represent the natural frequency of the system. There are two. One is 2 radian per second, and the other one is 1 radian per second. So now we need to find the mod shape function. What is mod shape function? Is when we apply the natural frequency to the system, how will the m1 and m2 move like? So we need to apply this equation of motion, k minus omega square times m matrix and times with the x double dot. So we replace the k and m and also the x into the matrix form. So we solve this 3 minus omega square x1 minus 2x squared. So now we replace the first, now we use the first natural frequency, which is omega equal to 1. Then we will get x1 is equal to x2. This is the mod shape function, 1, 1. It means that when the m1 moves to the right by 1, m2 also moves to the right by 1. If we apply the second natural frequency, which is omega is equal to 2, we will get x squared is equal to negative 1 over 2 x1. So the mod shape function is 1, negative 0.5. So when we apply this natural frequency into the system, when the M1 moves to the right by 1 unit, the M2 will move to the left by its half, is 0.5 unit because it's negative direction. It's negative value, it means the opposite direction. So this is all about me. Thank you.
So lastly, this is the application in electrical engineering. So in electrical engineering, you will face a state space representation or the first order linear time invariant system representation in matrix form. So with this equation, it will show the connection between input, output, and the system's condition in the circuit. So this is the general formula for the state space representation. Qt equals to AQT plus BUT, and also YT equals to CQT plus DUT. Q is a state vector, Q is a state vector, A is a state matrix, B is input matrix, U is input, C is output matrix, D is direct transition matrix, and Y is output. Next. So this is a diagram of diagram to find the state space representation. So before we do the calculation, we need to we need to choose the voltage across capacitor and current through inductor as state variables. So so using these two formula, we can get the state space representation. So if we can write equation for voltage across an inductor, it becomes a state equation when we divide by the inductance. So for example, if we have equation for E inductor and divide by N, it becomes an equation for di inductor over dt, which is one of our state variable. So if we can write an equation for current through the capacitor and divide by the capacitance, it becomes a state equation for E capacitor. Next. So we need to know that in this diagram, the input is IA and the output is E2. So there are three energy storage elements. So we expect three state equation. So try choosing I1, I2, and E1 as state variable. Now we want equation for the derivative. The voltage across the inductor L2 is E1, which is one of our state variable. So from there, we can get an equation of L2 times with diL2 over dt equals to E1. So we shift L2 from the left side to the right side, and we get our first state variable equation, which is diL2 over dt equals to 1 over L2 times with E1. Next. So from this diagram, we can also denote that the sum current into the node level N1 is IA minus IL2 minus IC1 minus IL1 equals to 0. Next. So the equation has our input IA and two state variable IL2 and IL1 and the current through the capacitor. So from this, we can get our second state equation, which is IC1 equals to C1 times with dE1 over dt equals to IA minus IL2 minus IL1. And we shift the we shift uh, the differentiation dE1 over dt to the left hand side and IC1 to the right hand side. So it became dE1 over dt equals to 1 over C1 times with IA minus IL2 minus IL1. Next. So our third and final state equation we get by writing an equation for the voltage across L1, which is E2 in terms of our state variable. So E2 is equals to L1 times with diL1 over dt equals to E1 minus R1 L1. So same like before, we shift the derivative to the left hand side and E2 to the right hand side. So it became diL1 dt equals to 1 over L1 times with E1 minus R1 L1. So um, by shifting the 1 over L1 to the left hand side, we will get E2 equals to E1 minus R1 L1. Why it becomes E2? Because if we can see that di over diL2 over dt uh, times with L2, it will become E2. Next. So from this, we get to know our state space representation. So with the general equation Q equals to AQ plus BU and Y equals to CQ plus DU, you will get this the state space representation. So uh, Q will be IL2, E1, and IL1. A is 0, negative 1 over C1, 0, 1 over L2, 0, 1 over L1, 0, 1, negative 1 over C1, R and negative R over L1. So C is 0, 1, and negative R. B is 0, 1 over C1, and 0. Lastly, D equals to 0. So that's all from us. Thank you.
Thank you.